Hello there, Mr. Sutton bringing you this lesson on antiderivatives, part 1. In this one, we're going to be figuring out the general antiderivative of basic functions. At this point, we're going to introduce a very important term, antiderivative. The antiderivative of f of x, which is given by this notation here, is the function whose derivative is f of x. It's basically the reverse derivative of f of x. So we've got this dx here that we're not going to really talk about too much right now. You just keep writing it inside this antiderivative notation. And we've also got this thing that kind of looks like an f, but it's actually a stretched out s. We'll talk about that a little bit later too. For now, just given that we're looking for the thing whose derivative is 4, try finding the antiderivative of 4. All right, let's see what you came up with. So what function do I have to take the derivative of to get 4? Well, if I had 4x, the derivative of that would give me 4. So the antiderivative of 4 is 4x, right? Well, not quite. It's actually 4x plus c. Now, what is that, you're saying? Well, c is just any constant, some constant. Now, if you don't believe me that this is the antiderivative of 4, we can prove it by taking the derivative of 4x plus c. If you do that, derivative of 4x is 4. Derivative of c is, you guessed it, 0. So you might be wondering, do we really need this plus c out there? That's kind of annoying and seems excessive. We actually do. That plus c covers the possibility that there was some constant that got differentiated away. So that plus c needs to be with every antiderivative that we take. Now that we've got the basic idea of what an antiderivative is, try these two out here. Pause the video, give it a shot. All right, let's see how you did. So let's tackle A first. What do I have to take? We'll go term by term here. What do I have to take the derivative of to get 3x? Well, using the power rule, I must have started with an x squared. So that 2 had to get multiplied by some number that would leave me with a 3 here. 2 times what would equal 3? Oh, 3 over 2, because then the 2's would cancel. So this used to be 3 over 2 x to the second power. And then this 2 we know was just 2x. And then we have that plus c. All right, let's try part B. So this used to be something times x to the third power. But when I multiplied this 3 back out using my power rule, I just got a coefficient of 1. So 3 times what would give me a coefficient of 1? Oh, 1/3. So this used to be 1/3 x to the third power plus c. On those last two problems, we were doing kind of an experimental guess and check sort of method for finding the antiderivative, but it'd be nice if there was just a systematic way of doing this that didn't require all those mental somersaults. And in fact, there is a way to reverse the power rule very quickly and efficiently. So here's the reverse power rule for the antiderivative of a times x to some constant n. A and n are just constants. So taking the antiderivative of that means we have to add 1 to the exponent and then divide whatever coefficient is here inside the antiderivative notation. We have to divide that by the new exponent of n plus 1. And this works as long as n is not equal to -1. Because if it was -1, well, you'd be dividing by 0, and we know that's a huge no-no. So just to put it in English, again, add 1 to the exponent and then divide the coefficient by the new exponent. So pause the video. Using this newfound mental technology here, give this antiderivative a shot. All right, going term by term. X to the third, bump that up to the fourth power. Then we divide the invisible 1 here by 4, so that'll be 1/4 x to the fourth. Ooh, much nicer than that weird reasoning we did on that last page, right? All right, next one. This is going to become the fifth power. Dividing by 5, we have 4/5 x to the fifth. And over here, this is going to become x to the eighth. Dividing by 8, we've got 2 over 8, or 1 over 4, x to the eighth power. Still don't forget that plus c. Here's a couple of oddball problems. What do we do when we have rational and radical functions? Well, what did you do when you were using regular power rule? Oh, that's right. You rewrote the rational and radical functions with either negative or fractional exponents, or both if you had both functions combined together. So let's do that over here on the left side. This is really going to be 2x to the negative 2. Just like before now, reverse power rule, we're going to make this negative 2 plus 1 in the exponent, and we're going to divide our coefficient by negative 2 plus 1, whatever that new exponent is. So this is going to be, let's see, 2 over negative 1 is negative 2, x to the negative 1 power, plus c, still there. And just be careful adding 1 to negatives and fractions. You're going to make this less negative. So there's our antiderivative for this problem. Over here now, let's rewrite this with a fractional exponent. This is going to be x to the 3 over 2 power over root. And now we're going to have to add 1 to 3 halves, and then we're going to have to divide everything by 3 halves plus 1. What is 3 halves plus 1? Well, that's really 3 halves plus 2 halves, or 5 over 2. So we're going to have 1 over 5 over 2 times x to the 5 over 2 power. And we're not quite done. If this is a multiple choice question, you better believe the AP exam is not going to write it like this. They're going to flip that, take the reciprocal. So this is really 2/5 x to the 5 halves plus c. Let's take a look now at some other common antiderivatives. Antiderivative of sine. Well, if I took the derivative of cosine, I would get negative sine. So that means the antiderivative of this is going to have to be negative cosine, because the negative that you get when you take the derivative of cosine has to cancel out with this negative to give us positive sine. Let's keep going now. Cosine, antiderivative is going to be sine, because derivative of sine is cosine. Secant squared, that antiderivative is going to be tangent. And these are all plus c, of course. And then cosecant squared, that one is going to actually be negative cotangent. If you just did derivative of positive cotangent, that would be negative cosecant squared. So we need a negative out in front there. For secant tan, that's really the derivative of secant. And then cosecant cotan, that's going to be negative cosecant. Now for e of x, what do I have to take the derivative of to get e of x? Oh yeah, e of x. E of x, or e to the x rather, is its own antiderivative and derivative. Kind of cool. But now b to the x is a little bit different. Normally when you take the derivative of b to the x, you get a b to the x times an ln of the base. So the antiderivative of this, we're going to have to divide by the ln of the base to cancel that out. For this one, we could try using the reverse power rule, but it wouldn't work very well. If you have x to the negative 1, your new exponent is going to be 0, but then you would be dividing by 0. So we need something completely different. This ends up being the ln of x plus c. And yes, that is an absolute value symbol around x. Why do we need it? Well, we're not allowed to take the ln of negative numbers. Not really allowed to do 0 either, but at the very least, negative numbers we don't want. If you tried doing reverse power rule on this again, you'd get 1 over 0, so we need this completely different shortcut for these types of problems. And then for this one, you might recognize this as the derivative of arctan, and then you have the other inverse trig functions as well. You'll want to recognize their derivatives, and then if you see that in the antiderivative symbol, you just give us the original inverse trig function. For your wrap-up problem, I just decided to throw everything, including the kitchen sink, at you. Have fun with this. All right, let's see what you made of this. I would recommend you start this by rewriting any fractional or radical functions with definitely negative or fractional exponents. So for this, we'll have 4x to the negative 1, although you don't really need to rewrite this particular one because, again, we have that different rule that we have to use for it. This one, though, is definitely going to be minus 8x to the negative 3. And over here, I'll write this as x to the 7/5. All right, going through one term at a time, 6, the antiderivative is just 6x. And then this next one, we bump this up to an exponent of 2017 and divide by 2017. For this one, this is going to be 4 times the ln of absolute value of x. This one, we're going to bump that up to a negative 2. Dividing by negative 2 gives us plus 4x to the negative 2. Over here, you might recognize 1 over the square root of 1 minus x squared as the derivative of arc sine. Since there's a 2 out there, this is going to be 2 arc sine of x. For this fractional exponent, we have to add 1 to the exponent. We're adding 5 over 5, so this becomes x to the 12 fifths, and then we have to divide by 12 fifths, which is really the same thing as multiplying by 5 twelfths. So careful, when you're dividing by a fraction, you actually end up flipping it and then multiplying. For this next one, secant squared, that's tangent, so this will be negative 7 tan of x. And then finally, this one's the toughest of all, right? E to the x, again, is its own derivative. Any constants out there are just along for the ride. So this is also going to be minus 1/4 e to the x. And we got everything? Oh yeah, plus c. This concludes our first lesson on basic antiderivatives. I know this doesn't look very basic, but if you look at each individual step of this, these were very quick and simple antiderivative sort of rules that we applied here. In the next one, we'll take a look at some not so simple expressions that we need to take the antiderivative of. Until then, this is Mr. Sutton signing off.